Now we're going to go into sections 5.3, which is exponential functions. This is an exponential function. That's what it looks like. And in order to understand what an exponential function is, we need to graph it. What else is new, right? Okay, so let's take values for x and y. And since I kind of know here what I'd like to do, I'm going to start down here, 1, 2, 3, 4, and then -1, -2. And you'll see why I kind of skewed this in the direction of positive values of x. You'll see why in a moment. Okay, so when x is equal to 0, 2 to the 0 is equal to 1. So x is 0, y is 1. X is 1. Y is 2. X is 2. Y is 4. X is equal to 3. 2 to the third equals 8. Let's put those in here. And you can see that we're going to go right through the roof any minute. That's what very often happens in these situations, All right, so obviously, at least this part of the graph shoots up very quickly. What happens on the other side? X is -1. 2 to the -1 is 1 is a half. So if this is 1, this is where a half is going to be. This is 2, this is 3, let's say. So when x is -1, let's make it -1 over there. And -2 is going to be equal to 1/2 squared, which is 1/4, which is going to be really, really small. And as you increase the x in the negative direction, the y's get very, very small. This is what it looks like. That's what it looks like. In other words, it sort of floats along the x-axis towards negative infinity, going very, very slowly, getting, as the values of x get very, very small, get very, very negative, the values of y get very, very small. It hits 1 at the y-axis, and then suddenly shoots up like crazy. That's what an exponential function is. Some situations where that's true. But let me continue for a moment. Y equals, y equals 2 to the -x is going to be, without going through the actual graphing of it, we know that it's going to be the reflection in the y-axis. So this is going to look like this. This is called exponential growth. This is called exponential decay. There is this certain matter in science which grow very quickly and certain that decrease very quickly. And that's what they look like. All right, now, we're not going to spend too much time talking about exponential functions, but we will talk about how to transform them. This is what the typical graph looks like of an exponential function. Let me get that exactly as I have it. A to the n to the x minus h plus k. So there it is back again. You know, the a, the k, the h, the k. And whether we, move it left or right or up and down will be dependent upon the h and the k. The h will tell us how far we move it to the left and the right. The k will tell us how far we move it up and down. Let's take an example. 2 to the x minus 3. Okay, so in other words, if we look at the original exponential graph as the parent function, or let me clean it up a little and just simply say that this is what the parent looks like, right? And it goes up more severely than that. So this would be that down here at -3. Y equals -3 becomes the new x-axis. Usually the x-axis is y equals 0. We're saying that this, the new x-axis is going to be down there. And then it becomes important for us to, but the x equals 0 stays the same. Okay, that's the y-axis. And let's see what this looks like. So let's again take values of x and y. So when x is equal, let's use 0 and 1, because we're still using the y-axis here. So when x is equal to 0, 2 to the 0, 2 to the 0 is 1, minus 3 is -2. So it's always going to come up like this. But at -2, it's going to make its crossover. And you know what happens when it hits -2? It then should shoot way up. When x is equal to 1, 2 to the 1 is equal to 2, minus 3 is equal to -1. 2 minus 3 is -1. So when x is equal to 1, y is equal to -1. So it's going to look like, this is what it's going to look like going in that direction. And you'll see that we do indeed have an asymptote. And the asymptote will be, as we might have expected, y equals k, as it always is. In this case, the asymptote was y equals -3. In the original case, it was y equals 0. So we can move this thing up and down. But it only has, and I should write this as a rule. As a rule, exponential graphs only have horizontal asymptotes. Right? I mean, we're not talking, we've graphed so far 4 of these graphs. Y equals 2 to the x, y equals 2 to the -x, y equals 2 to the x minus, 3 of them. And in all 3 of them, it had a horizontal asymptote. It never has a vertical asymptote. It always looks like this. The only question is how far down it goes, how far up it goes, how far to the left does it go, how far to the right does it go. And that'll be dependent upon all the other factors that we usually take into consideration. For example, again, let's take a graph that looks like this. let's take y equals 2 to the x minus 3 plus 1. Okay, so the plus 1 would make sure that the new horizontal asymptote is 1, but x equals 3 is going to be the new y-axis. So x equals 3 is the new y-axis. Okay, so it's actually going to come this way. And then at 3, 3 minus 3 is 0. 2 to the 0 is 1. 1 plus 1 is 2. So this is where it's actually going to cross the y-axis right over there. And then it's going to shoot up like that. So that's what that's what I forgot. I forgot the h. The k is equal to 1, and that's where that comes in. But the h is equal to 3. So that's where and it's not an asymptote, but that's the new y-axis. That's what this was at x equals 0. It's now x equals 3. All right, so that's what happens with the x and y. The y creates a new horizontal asymptote, and the value of x is where it actually crosses that axis. So and when x is equal to 3, 2 to the 0 is 1, 1 plus 1. So this is the point 2. And then you can go on from there. When x is equal to, that's what was going wrong. When x is equal to 4, 2 to the 4 minus 3, 2 to the 1 is 2 plus 1 is 3. So that'll be over there, and it'll just shoot up like that. To do a graph like this, negative x minus 3 plus 1, then it's probably, one would think it's going to be a reflection. So everything that's true for a regular graph is true for this one as well. All right, and we're not going to spend too much time on exponential functions, except to just state that this is what they look like. And this is the general formula right over here. Let me make sure that you see that. Right, and you can do various things to either make it higher and lower, or you can move it up left and right. And again, keep in mind that the negative really means a positive, and if this happened to be a positive, then it would be a negative. All right, so it would be over here instead of over there. And that's what an exponential graph looks like. And I'd like to go on now to section 5.4. Know what an exponential function looks like. And now we're going to take a look at a logarithmic function. A logarithmic function. So this is an important section because we're actually taking a very close look at the relationship between an exponential function and a logarithmic function. So a logarithmic function, first of all, go back to the exponential function. Now, it just happens to turn out. Now, remember what the inverse was. The inverse was a function which reflects across the line y equals x, x equals y. And remember that an exponential function looks like this. So it would be logical, therefore, to assume that if we took this graph and we flipped it over, because this is kind of like the point of reflection, x equals y, it would come like this and go off in that direction. And that would be what the inverse of this looks like. So this, if the function is y equals 2 to the x, let's see what the inverse would look like. Graphing it is not difficult because we can see what's going to happen. It's going to come like this, and since this is a reflection, this is going to come like that, And the inverse is actually going to have a vertical asymptote. The original function has a horizontal asymptote, but the logarithmic function has a vertical asymptote. You can see it's coming up that way and going off like that. So this is the exponential function. And this is the logarithmic function. But let's see, how that came about. What is a logarithm? Well, if we were to find, so we know that this is what the inverse looks like. So let's see if we could do it algebraically. So the way we do it, of course, is this way, right? We replace the y with the x, so now x is equal to 2 to the y. And the problem here is that there is no way for us to solve for y. There's no way to solve for y. Mathematically, we cannot solve for y. Therefore, when mathematics confronted this hundreds of years ago, they came to the conclusion, hey, we need a way of expressing the inverse. There is no way of finding out what y is equal to. So we have to create a new function. And that new function is going to be called a logarithmic function. That's where logarithm comes from. It comes from the inability of mathematicians to be able to find the inverse of an exponential function. And now the question is, so what is this as a logarithmic function? This is what it is. And the abbreviation for logarithmic will be log base 2, so the 2 will go down here. This is called the number. I call it the number. So I call this the number. But if you look at books, they call this, and I don't know why, that's what I was doing during the break. I was trying to figure out why this number is called the argument. It made no sense to me. I mean, you can't even, there could have been an argument as to why there was no way of solving for it, but it's called the argument. We could call it the number. And this is going to be called, and the x is going to be called the exponent. So what we need to do during this section is we need to be able to go from exponential functions to logarithmic functions and the other way around, from logarithmic functions to exponential functions. And this is actually what the homework is all about. And I'd like to take a look, therefore, at page 106. So 106 has a bunch of problems. If you're looking at the workbook now, you can see that. If not, I could just tell you that there's a bunch of problems. And the first one, the first part on page 106, part B, it's part B, section 1. And all of the problems, except the ones that are for homework, we're going to take a look at those. So this is the first problem. 1A. 5 to the third equals 125. First of all, is this true? And the answer is yes, because 5 times 5 times 5 is indeed equal to 125. So we know this is a true statement. And the question is, how do we express this exponential function into a logarithmic function? And the way we do it is the way I was showing you up here. This is going to be log. Now, what's the base? The base is 5. That's this number right here. The number with the exponent attached to it is the base. So that's 5. The argument, which we are going to call the number, is 125. And the exponent is 3. This is the process of changing from an exponential function to a logarithmic function. Very simple process, really, what I just did. As long as you remember that the base goes down there, the number goes over there, and the exponent goes over there. When we talk about logarithms, we are really saying that the log of a number to a certain base is equal to an exponent. The logarithm of a number is a log is an exponent. And here it is right here. We're saying that everything works out, and that's going to be the log. Here is problem. This is very similar. Do a couple of very, very similar and easy problems. So here's another example. I'm going to do this with you again. So the log, in this case, to the base 3, the argument is 81, and the exponent is the answer, and that's 4. Going from an exponential function to a logarithmic function. And I'll leave, and this is one for you to do. Well, I don't want to just make it extremely difficult too quickly. So let's just take a very simple problem. Let's take G. Same kind of problem, basically, but different numbers. Change this exponential function into a logarithmic function. I mean, that's all the time you really need, because this is going to be the log to the base 4 of 64 is equal to 3. That's how easy it is. And the only thing that makes it a little more difficult is they give, kind of complicated problems. Like problem C is 1 over 32 equals 2 to the negative 5. Okay, so the instructions are change that into logarithmic form. Log, the base is 2, the number is 1 over 32, the exponent is negative 5. Okay, that's all it is, changing from exponential form to logarithmic form. The next part of what we're going to be doing is the opposite. Going from logarithmic form to exponential form. Okay, so now we're going backwards. And let me take a typical problem. These are on the same page, but section 2. And here's an example. Log to the base 10 of 100 is equal to 2. Running out of time. And I'm going to do this with you, and then you could do a couple of these, but let me just do the first one. So in other words, the base to the exponent is equal to the number. And that makes sense because 10 to the second power is 10 times 10. 10 times 10 is 100. Okay, that was problem A. That was the very, very first problem. Okay. And I'll let you do the next one. Problem G would be log to the base 5, 125 equals 3. And also, I will ask you to do problem K, which would be log to the base 8 of 1/64 equals -2. So the instructions are for these two problems, change to exponential form. Okay, I think you should, I mean, this is really, you know, I must say, nothing in this course is easy, but this is just not that difficult. The base to the exponent equals the number. That's all they want you to do. You know, they don't want you to figure anything out. They're telling you what the numbers are. All they want you to do is convert it from one form to the other, which is an important concept. And then this one would be 8, which is the base, to the -2 is equal to 1/64. Okay? Does anybody have a question so far about being able to go from exponential to logarithmic, logarithmic to exponential? Is there a question? Okay, then we have one last thing to do. So let me get some room up on top, because you're going to need some room in this case. So, you know, when you think of logarithms as being inverses of exponential. A logarithmic function is simply an inverse of an exponential function. It's just written in a very peculiar way because it's just more difficult to be able to solve for y. But in general, that's what a log is. A log is the inverse of an exponential function. I'm not even sure we're going to need all the space down here because the problems. So how much time do we have? It's about 4:20. So we don't really have a lot of time, but let me just give you a problem to do. And I'm going to ask you to do this on your own. This is on page 106. And this is actually what the homework consists of. 106, 3a. And this is log 3. The number is x, and the exponent is 2. Solve for x. And after about 3 minutes, I'm going to give you a hint, because you know you might be saying, "How do you do this?" And I'd like to give you a hint as to how you would do it. But I'm going to give you first. I'm going to let you kind of brainstorm with yourself and see if you can figure that out. Step 1 should be to convert this logarithmic expression to an exponential expression. So the base to the exponent equals the number, unless you already figured that out. And the answer is turning it around, of course, as I like to do. X equals 9. 3 squared is 9. Okay, so that was a pretty easy equation. This is a little more. Is there any question about that? Should ask that question, right? Okay, then the last problem of the day. Don't run away after this is over, because I do have to say something to you. Solve for x. And this is a little more difficult. but a very, very challenging problem. Okay, so take a moment and see if you could do that. Let me start you off here. This is kind of a difficult problem. I remember from last semester. This is what it is. This is what it is. In other words, what number raised to the negative third power is equal to 8? Does anybody know how to do this, or at least how to, start it? Anybody?
All I can think of is since it's negative exponent, so it's 1 over x to the power 3 equals 8. Is that correct?
Say it again. Let's take this problem and rewrite it.
Okay, it's 1 over
Hey, whoa.
Oh.
Go ahead. You want to
1 over.
Okay.
Yeah.
Let's explain what you're doing. You're trying to get the x by itself, right?
Yeah.
Yes.
So yeah, so I'm trying to
So
since
you're
it's a
raising
negative
it to
exponent
what power?
to the third.
Yeah, but how about
Yeah,
the negative?
well,
What are you going to do about
okay.
the negative?
You did like that. Yeah. No, I just converted it to the fraction, and then
Okay, what you should do then? Well, okay, we don't want it to be. All we want is x to be by itself, without any exponents. So in order to do that, you have to raise it to the negative 1/3. Understand what I'm saying? This is x to the negative 3 over 1. To make the x by itself, we need to raise this power to the reciprocal power. And we have to do it on both sides. You didn't do that?
yeah, that's where I got stuck. I'm like trying to figure out.
Yeah, well, that's why you got stuck. You got stuck because you made this into a fraction, and then you didn't quite know what to do with it. But you can
Yeah.
get rid of that fraction part by just raising it to the negative, and the negative times the negative would cancel each other out and become positive, and then you just have to worry about that being negative. So that's what you do. This becomes x to the first, or just x. Get it? I hope.
Yeah.
This becomes x to the first. This is what gets made into a fraction. 1 over 8 to the 1/3. What is 8 to the 1/3?
2.
Good.
Yeah, the cube root of 8. Yeah.
There it is. That's the answer to the question. Whoops. Good work. Good work by 2 of the best students in the class. Good work. Very, very, very nice. We all work together in this one. So what Vincent was trying to do was good. He was trying to raise the 3 power to the 1 over 3 to get rid of the 3. But he got into a mess because he still had the negative, which made the x into a fraction. So he actually wound up with, if I might, Vincent, I think you wound up with 1 over x.
Over, yeah, something like that. Yeah, 1 over x to the third power.
Oh,
That's
no,
what I was trying to do it like that.
One over, yeah, this
Like that, yeah.
equals that.
Yep, that's what I was trying to figure out.
But you had to raise that also to the, no, that's not gonna get you.
Yeah.
All right, okay. But anyway, that's how you would do it.